Hello, we're going to start off today talking about resonance and resonance structures. So resonance occurs when a molecule with a double bond, has to be a double bond, may have that bond in more than one location. So I think we drew a Lewis structure for sulfur trioxide already, and I kind of alluded to this. So let's take a look at a Lewis structure for this molecule. So we have 24 valence electrons, minus 6, we got 18 leftovers, distribute them to the bonded atoms, and then what we'll see is that sulfur is short of an octet, and so we need to make a double bond. So I asked this before, so where does the double bond go? Top, left, right? Exactly, goes anywhere. So I'm going to put the double bond there, my lone pairs of electrons, and usually we put a kind of double arrow in between the different resonance structures for a molecule. So double bond could go bottom left, it could go bottom right, or it could go at the top, top oxygen, if you will. So you have three equivalent Lewis structures. They're all the same, except the double bond is in a different location. So if you run into this situation where you're asked to draw the resonance structures, draw all three, or however many there may be only two or three different Lewis structures. Now, in reality, so where is the double bond in reality? Which oxygen has the double bond? In reality, none of the oxygens have a true double bond. So what happens is these electrons here that make up the double bond are said to be delocalized, meaning they can move around between all of the oxygens. And so maybe a better way to, or another, I shouldn't say better, but another way to draw the resonance hybrid is called for something like sulfur trioxide. Looks like this. And then we used kind of the dashed line. Oops, can't really see it here. Here, I'm going to start over. Let's redo that. And we use dashed lines to show those delocalized electrons. Again, the electrons that make up the pi bond, we'll talk about pi bonds next. The electrons that make up the pi bond are able to move around between sulfur and all three of the oxygens. So that's what resonance structures are. We'll do some more examples later on. All right, speaking of pi bonds, we have two types of bonds between atoms. These are referring to a situation where we have covalent bonds. We can further classify them as sigma or pi bonds. So here's how it works. The first bond formed between atoms that form a covalent bond is a sigma bond. Now let me jump ahead a little bit. This will make more sense after our next lesson. Sigma bonds results from the overlapping of hybrid orbitals. So we'll talk about hybrid orbitals next time. When two hybrid orbitals overlap, or when one hybrid and one atomic orbital overlaps, that bond is known as a sigma bond. Says that the electrons shared between the atoms that form this bond are found in the region between the nuclei of the bonded atoms. All right, so I'm going to show you an example of a molecule that has both sigma and pi bonds, and we'll be able to look at both of them. That molecule is C2H4. So go ahead and pause the video and draw the Lewis structure for C2H4. Do that now, please. Here's that Lewis structure. We have a double bond between two carbons. We got single bonds between carbons and hydrogen. So let's take a look at what's going on in this situation. All right, so again, just looking ahead a little bit, we have some hybrid orbitals that form. Don't worry too much about that yet. But what I want to point out is this. So the orange here represents the hybrid orbitals of the carbons. And then where we see where the orbitals Those hybrid orbitals of carbon overlap. That creates something called a sigma bond. Also, when we have overlapping of hybrid orbitals of carbon and atomic 1s orbital for hydrogen, we also have a sigma bond. So again, first bond, if you will, that forms between two atoms that have a double or triple bond is a sigma bond. Technically, sigma bonds result from the overlapping of hybrid orbitals with other hybrid orbitals, or hybrid orbitals with, in the case of hydrogen, atomic orbitals. So how about pi bonds? So the second bond of a double bond, or the third bond, second and third, if it's a triple bond between atoms, are pi bonds. So first one, sigma, so you got one sigma bond, and then one pi bond if it's a double, one sigma, two pi bonds if it's a triple bond. For pi bonds, the electrons shared between the atoms are found in regions above and below the plane of the sigma bond, and side to side or front to back, however you want to look at it, of the sigma bond as well. There's also a diagram in your book on page 331, and it shows the same thing that I showed you before. So let's look again at a situation where we have C2H4. So we have the sigma bond here, results from overlapping of the hybrid orbitals of carbon. These green here represent something called unhybridized p orbitals. So we can see that in this diagram, we have three hybrid orbitals, and we have this is actually just one atomic. This is actually a 2p unhybridized orbital. And so what happens is the unhybridized p orbital of the carbon on the left and the unhybridized p orbital of the carbon on the right, they overlap. Notice both above and below the plane of the sigma bond. So let me label our sigma bond here. So we have a sigma bond here. And then we have overlapping of the p orbitals both above and below the plane of the sigma bond. That is our pi bond. Now, if you have a triple bond between atoms, you would have two unhybridized p orbitals. And we can see that on page 331 on the bottom. Two unhybridized p orbitals overlap, forming two pi bonds. So a triple bond consists of one sigma, two pi. Double bond, as we see here, consists of one sigma and one pi bond. Take a look at some examples. What I want you to do is to draw the Lewis structures. Now we'll do this one at a time. Draw a Lewis structure and determine the total number of sigma bonds and pi bonds in each of these molecules. So we'll start with carbon dioxide. Go ahead and draw the Lewis structure. Do that now. Pause the video now, please. So in carbon dioxide, we have two double bonds. So how many sigma, how many pi? We have two sigma bonds and two pi bonds. So one of these is a sigma, one's a pi. One of these is a sigma, one is a pi. All right, next one, draw a Lewis structure for nitrogen, diatomic nitrogen. Pause the video now. For nitrogen, we have a triple bond. So how many sigma, how many pi? We have one sigma bond and two pi bonds. So one of these is sigma and the other two are pi bonds. All right, next, draw a Lewis structure for HCN. In this case, we have three different atoms. Carbon is the central atom. So go ahead and draw that Lewis structure. Pause the video. Sigma bonds, we have a sigma bond here. One of these is a sigma bond, so there are two sigma bonds. And then the other two bonds of that triple bond are pi bonds. So two sigma and two pi bonds. All right, last one, go ahead and draw a Lewis structure for sulfur dioxide. Any one of the resonance structures. So sulfur dioxide exhibits resonance. So just draw one of the Lewis structures and indicate the number of sigma and pi bonds. Pause now. All right, total sigma bonds. We have a sigma bond here. One of these bonds is also a sigma bond, so two sigma bonds. And then one of those that make up the double bond is a pi bond, so two sigma and 1 pi bond. All right, let's go ahead and add a section to the notes. This is not in the notes, so anywhere you have room, let's add this. So we have something called bond order. There's these things called properties of a covalent bond: bond order, bond length, bond energy. So here we'll just cover bond order. Pretty simple. Bond order refers to the number of bonds between bonded atoms. It gets a little complicated when you have molecules that contain more than just 2 elements, or 2 atoms, I should say. So we'll start off simple. So it says a single bond has a bond order of 1, a double bond has a bond order of 2, and a triple bond has a bond order of 3. So let's take a look at some examples, and I'm just going to draw Lewis structures for you. So consider the molecule chlorine. What is the bond order in chlorine? Well, we have 1 single bond, so we would say that the bond order is 1. Now let's take a look at Lewis structure for oxygen, diatomic oxygen. In this case, the bond order is 2. We have a double bond. And you know where I'm going next. Bond order of bond order in this molecule is 3. So like I said, it gets a little bit more complicated, complex, if the molecule or polyatomic ion contains more than just 2 atoms. So here's how it works. To determine the bond order in a molecule where you have more than 2 atoms, you're going to take the number of bonds, total number of bonds in that molecule or polyatomic ion, works for polyatomic ions as well, and then divide that by the number of bonded atoms. So let's go back and take a look at carbon dioxide. So carbon dioxide has 4 bonds, if you will, 2 double bonds. 4 bonds divided by 2 bonded atoms. The bond order in carbon dioxide is 2. Let's take a look at the Lewis structure for carbon tetrachloride. I know I'm leaving off the lone pairs of electrons. I'm just focusing on the bonds here. Bond order in carbon tetrachloride, we have 4 bonds divided by 4 bonded atoms. The bond order is 1. How about sulfur trioxide? Go ahead and pause the video and determine the bond order in this molecule. Do that now, please. All right, so this time we have 4 bonds, 2 single, 1 double, so it's going to be 4 bonds. Divided by 3 bonded atoms, we get a bond order of 1.33. Now that seems kind of weird, a bond order of 1.33. Well, think about what I showed you earlier and what we discussed earlier about those delocalized electrons. So in reality, the electrons that make up the pi bond in this molecule spend 1/3 of their time between sulfur and this oxygen, 1/3 of their time between sulfur and this oxygen, and 1/3 of the time between sulfur and this oxygen. Thus, we get a bond order of 1.33. All right, let's try one more. Go ahead and either redraw or look at the Lewis structure for sulfur dioxide. Here it is again. Go ahead and pause the video and determine the bond order in this molecule. So this time we have 3 bonds total divided by 2 bonded atoms. Again, we don't count the central atom. 3 bonds divided by 2 bonded atoms. We get a bond order of 1.5. So again, remember, we could draw resonance hybrid for sulfur dioxide like this. We're not going to do this, by the way, in this class. I just want to show you. Those dotted lines again telling us that sometimes the electrons of the pi bond are found between sulfur and this oxygen, sometimes sulfur and this oxygen. And so the electrons that make up the pi bond spend half their time between sulfur and each oxygen, so we end up with a bond order of 1.5 for this molecule. All right, this concludes this lesson. Next time we will continue with hybridization, the formation of hybrid orbitals. Thanks for watching.